We've seen that double integrals can sometimes be made easier by changing to polar coordinates. And triple integrals can sometimes be made easier by changing to cylindrical or spherical coordinates. I now want to explain how more generally you can change variables to any coordinate system you like. And to warm up to this, we're first going to review how this works in single variable calculus. This is sometimes called U substitution, although that's, I think, a kind of silly name because you can substitute any variable you like. It doesn't have to be called U. Anyway, as you probably remember, if you have an integral of some function f of x from a to b, which you'd like to evaluate, and if it turns out to be difficult or impossible to evaluate directly, it sometimes helps to replace the variable x by a new variable u. And formally what's happening is that x is actually a function of u. So if our x interval from a to b is over here, there's a u interval from c to d over here, and this u interval is mapped to the x interval. So x is some function g of u. And let's assume that g of c equals a and g of d equals b. Then the substitution rule tells you that its integral is the integral from c to d of f as a function of u, more precisely f of g of u, times g prime of u du. And the way this is presented in single variable calculus is you think of g prime of u du as dx du times du. And then heuristically you can cancel the du's, so this just equals dx. And then, so this integrand is the same as that integrand, and then you just have to remember to also change the limits accordingly. In multivariable calculus, things are more complicated and we can't just blindly cancel out stuff like this. But this is a good mnemonic for the single variable case. Okay, this also works if c is bigger than d. So it's sort of a strange thing to think of integrating from a bigger number to a smaller number, but the formula is correct if you interpret the integral from c to d as minus the integral from d to c. Alright, so why is this true? Well, you can prove it pretty quickly using the fundamental theorem of calculus in the chain rule. So you say that if you have an antiderivative of f with respect to x, then it's also an antiderivative of this expression with respect to u. However, that proof will not generalize to the multivariable case. So I want to show you a different way of understanding this. And to do that, I'm going to make an additional assumption, which is not really necessary in the single variable case, but will be necessary in the multivariable case the way we're doing it, which is I'm going to assume that each point in the interval from a to b corresponds to exactly one point in the interval from c to d. And then, what's going on in this formula? Well, if I think of the integral as the area under the graph, so here's over x, I have the interval from a to b. I have a graph, maybe it looks like this. And here I have the interval from c to d, and maybe my graph looks like this. So if you take some, we want to find these areas. Okay. If you take some little interval in u, say of length delta u, then this gets mapped to some interval over here of length, say, delta x, and the length of delta x is approximately g prime of u times delta u. So g prime of u is measuring how much this interval is getting stretched. And then if you look at the area of this little piece of the graph, well, that's getting stretched horizontally by this factor g prime of u. So the area of that piece of the graph is getting multiplied by g prime of u. So that's why you need this g prime of u to get the correct area. So you can think of this g prime of u as a magnification factor. Okay, now if you want to prove this a little more formally, it looks as follows. I'll show you on the next page. So what's the integral from a to b of f of x dx? Well, we divide the interval into n subintervals, so x0, x1, up to xn, like this. Before, I said that the lengths of these subintervals should each be 1 over n of the length of the whole interval, but in general, you don't really need that, so let's relax that, and let's just denote the length of the ith subinterval by delta xi. So this is xi minus 1. And then this integral is the limit as the maximum length of a subinterval goes to 0. That's going to require n going to infinity, of the sum from I equals 1 to n of f of xi star delta xi, where xi star is the sample point in the ith subinterval. Okay, now what about the u integral? Well, I do the same thing. So the integral from c to d of f of g of u, g prime of u du, so I write c equals u0 less than u1 less than up to un, which is d. So I take the limit as the maximum of delta ui goes to 0 of the sum from I equals 1 to n of f of g of ui star times g prime of ui star delta ui. So delta ui is ui minus 1, and this ui star is some sample point in the ith subinterval. Okay, so how am I going to relate these two sums? Well, first of all, I can choose my subintervals to match up. So if the interval from a to b is over here, and the interval from c to d is over here, then I can arrange that ui minus 1 and ui are mapped to xi minus 1 and xi. So I can assume that g of ui equals xi. And I can also choose my sample points to match up. So if this is the sample point ui star, I can assume that it is mapped by g to the sample point xi star over here. So this map is g. So g of ui star equals xi star. And then we have to think, well, how does delta xi relate to delta ui? Okay, so, well, that's given by this stretch factor. So delta xi is approximately delta ui times the derivative dx du. And where am I going to evaluate it? Well, I might as well evaluate it at a sample point in this interval. Okay, so we've arranged that this equals f of xi star, and I've arranged that this expression, g prime of ui star times delta ui, is approximately delta xi. And then in the limit, this approximation gets better and better. You need some justification to really justify that, but then in the limit, this sum becomes exactly the limit of this sum. So that's the proof that these two limits are the same, and hence these two integrals are also the same.